This is part 3 of the tutorial about type classes. In the previous part, I discussed the examples and the connection between type classes and algebraic data types and object-oriented interfaces. And then it was clear that algebraic type classes are related to algebraic data types, and co-algebraic type classes are related to object-oriented interfaces. Now, the main reason why we're looking at this is because the type class derivation patterns are very different for algebraic type classes and for co-algebraic type classes, so they have to be studied separately. We begin by looking at algebraic type classes. And for now, we will not look at type class laws. We just look at the type signatures that have to be implemented. So for example, if A were a type that belongs to a certain type class with algebraic type signature, and if B is a member of the same type class, it means we have structure maps P and Q given of these type signatures. So we ask the question, what other types C can we construct such that C is again a member of the same type class, so that we can derive, hopefully automatically derive a function R of this type, PC to C, where P we want to treat as an arbitrary unknown but fixed functor. So we want to do this generically with respect to P. And this is how we put this question. So it's a kind of a structural analysis of function types of this sort to see how can we create new function types of this sort from previous ones. And here are the patterns that exist, that are known. Well, the simplest one is that the unit type, so C can be just a unit type. And then we just write a constant function that returns a unit type, ignoring its argument, and that's certainly going to be a member of the type class. So a unit type is always a member of the type class. And as for the laws, clearly all laws are going to be satisfied. Any kind of law is going to be an equation using this function, but this function can only return a unit type. And so the left-hand side of the law is going to be a value of the unit type, and the right-hand side of the law is going to be a value of the unit type no matter what you do with this function. And that's always going to be equal. And so any law is going to be always satisfied by this. And so then I said we aren't going to look at the laws, but I just want to show you that actually you can reason about the laws. We will develop more sophisticated techniques for dealing with laws, but this is a specific simple case where clearly the laws will be satisfied too. The next case is if you have a function from some type D to A, where D is a fixed type that doesn't necessarily belong to the type class, but A does belong to the type class. Then so what we need to implement is a function with this type signature, because we are given this P and we want to construct the type class instance for this type now. And to do that, we just need to construct a function of this type. And this can be implemented because you take D, you have a function PA to A, you take this value, you do an F map on this value, substituting D into the argument of the function here, and then you get a value of type PA, and then you map it to A using the given function P. So that is how you implement it. So this is kind of trial and error. You write down some type and you try to implement and see if that works. So for instance, the type function a to d would not work. You would not be able to implement p of a to d to a to d, because p of a to d you could transform into p of d, but you don't have p of d to d. You only have p of a to a. D is not necessarily a member of the type class. So you can try some more things and you won't find any more patterns of this sort. Another pattern is a pair. So if you have a and b both in the type class, then the pair is also in the type class, because you can implement this function by just projecting fmap first, and that gives you, from this, it gives you pa, a value of type pa, and then you get a from it by applying p, and similarly you get b. So because you can implement this function, you have implemented automatically the type class derivation. But notice that if you wanted to try either a, b, so the co-product instead of product, then you wouldn't be able to implement the general code, because you cannot generally map p of either a, b into either of pa, pb, which would be necessary. For some p this is possible, but not for general arbitrary functors p. So for this reason, the co-product is not a general type class derivation pattern for algebraic type classes, but products are. And we will see later that for co-algebraic type classes, it's the opposite. The either is a general type class derivation pattern, but the product is not working in the same way. Actually, it's a different pattern that the co-algebraic types have. The next derivation pattern is for recursive types. So how do we describe recursive types? Recursive types are described as fixed points of functors. Now, this is a very much type theoretic point of view. Usually in programs, you you declare recursive types directly. You don't derive them as fixed points. It's inconvenient to do that. You can, but it's inconvenient. It's much more convenient to define a recursive type directly. Similarly to what happens with type classes, it's inconvenient to define type classes using a single method of this sort. It's inconvenient for practice. You usually need some parts of this to be used separately with different good names. So for practical programming, it is not very convenient to define type classes through the single structure map, but for reasoning about type classes and proving and exploring their properties, it is much more convenient. It's much simpler to just write down a formula like this, and then you just define new code, and you show that it is possible. But similarly with recursive types, it's much easier to deal with recursive types from a theoretical point of view and to prove their properties if you define them as a fixed point. So what is a fixed point? From the programmer's point of view, this is what it means. You have a covariant functor f, and then the type c is a fixed point of f. If you have functions that convert between c and fc, and these functions are inverses to each other, so their composition in both directions is identity. In other words, the types fc and c are equivalent in a one-to-one correspondence as types. And if that is the case, then c is called a fixed point of f. The intuition is that you apply f to c and it doesn't change. You get again the same type. But actually you don't have the same type. You have a type that is equivalent, is in a one-to-one correspondence. So the type fc is not the same type as c. It's a different type, but it's equivalent. So you can always transform values between them with no loss of information in both directions. That is the programmer's view of a fixed point. And this fixed point, it could be the least fixed point or greatest fixed point. I'm not going to talk about it right now. It doesn't matter. This definition covers all of those fixed points. So it is not true that there's only one fixed point. In other words, only one type C with these properties. For a given f, there could be many different types C with these properties, with fixed and unfixed defined in different ways. And we just assume that somehow these are defined, and then we prove that C can belong to the type class if f has a certain property. And that's all we need to prove. And then we have proved it for all kinds of fixed points at once. So what is that property that we need for f? We need a property that f should preserve the type class membership. In other words, whenever there's a type t that belongs to the type class, then the type ft also belongs to the type class. And that means if t has an evidence, so the type class evidence is this value of type pt to t, or structure map value. So if we have this value, then we can derive the structure map for ft. In other words, we require that there must be some function h with this type signature. And we assume that this function is given. Somebody needs to find out if that function exists for some specific f, a specific p. But that we assume this has been done, and indeed we have such a function. So if we do, then we can show that C belongs to the type class. So any fixed point of f belongs to the type class. So how do we show that? We implement the structure map for C by first taking fmap unfix. So fmap inside of P, we unfix, which means we transform C to FC. So that means we, instead of PC, will have PFC, P of FC. Then we apply to that the HR. So R is again the same function. So we are defining R recursively through itself. So H of R is a function of this type, which is then going to be used to transform P of FC to FC. So the result of this is FC, then we can apply fix, and we give C. We get C. So that is how we can implement the structure map for the fixed point. Now this definition is recursive, and in order for this to make sense, to converge, we probably need a lazy function evaluation. But assuming that all that works, and in case this recursion terminates, then this will be the correct function. So at this point, we cannot prove that the recursion terminates, because maybe it will terminate for some fixed points, not for others, or maybe if you have lazy evaluation, it will terminate, but if you have strict evaluation, you won't terminate. This is beyond the scope of what we're doing here. We just check that in case everything converges and sufficiently lazy, then we can implement a type class evidence for R, for this, for C, for the fixed point. The final derivation pattern is the so-called free instance. So what does it mean? A free instance, so I'm generalizing here from what you probably know. There are free monads, free functors, free monoids, free applicative functors, and so on. So this is generalized to say there's a free instance constructor for a type class, for an algebraic type class. So it turns out that algebraic type classes have a free instance constructor, which is a functor, certain functor m, let's call it m, with certain properties. And the properties, for instance, are that for any type t whatsoever, the type mt belongs to the type class. So it has a structure map where t is arbitrary. It doesn't have to belong to the type class. So this type constructor m needs to wrap the type t in appropriate stuff so that the result, the type mt, belongs to the type class. It has the structure map. And satisfies the laws, of course, too. And then another property that is necessary is that for any type C that belongs already to the type class, we can compute MC to put C inside this free instance constructor, which is not necessary, right? Because C already belongs to the type class, but we can do it anyway. But if we do that, then there must be a unique way to get back to C from this. So wrapping a value of a type that already belongs to the type class is equivalent in some sense to not wrapping at all. So this wrapping is transparent and unnecessary. It can be removed. So this function that removes the wrapping must be unique and type class preserving. Now the property of type class preserving, I will explain it in the next part of this tutorial. It's a somewhat technical property. It means that this map removes the wrapping in a way that preserves the structure of operations in this type class. So operations are all described by the functor p. And so this is a technical property that I will discuss in detail in the next part of the tutorial. And there are some other technical conditions which I don't discuss here. But essentially, if a functor m exists with these properties, then it is called the free instance constructor for that type class. And here are some examples. A free monoid is just the list type constructor. So if I have any type t, then the free monoid on t is list t. And list t is a monoid for any t. And if you have any monoid, then list of that monoid can be folded to a single value of that monoid. So this map is just a fold for the list with the monoid, or reduce, as it's called. I believe it's called reduce, not fold. So reduce from list of C to C, where C is a monoid. And another example is free monad. So free monad is a type constructor which is higher kinded. It takes a functor and returns another functor, which is free monad f, and that is defined recursively like this. Now, this is certainly not trivial that this is actually true, that this is a monad is relatively simple to see, but that there is a unique type class preserving function when f is already a monad and you put f in there, and then you need to prove that there is a unique monad preserving, or as it called in category theory, monad morphism, monad preserving function from this to f. That is not so trivial to prove. I'm not going to do it here. I'm just going to say that you can find usually the constructor m for most type classes, but you have to find them for each type class separately. There is no recipe that gives you the free instance constructor for any given type class just as a function of p, say. There is no such recipe, except when the type class has no laws. So if there are no laws at all, then actually turns out that free monad p as a type constructor is the free instance constructor for an algebraic type class with the structure functor p. I'm not going to prove that, but I will in the book. So that concludes the derivation patterns for algebraic type classes. Let me remind you what we have seen. So there are these type class derivation patterns: unit type, function type, pair, recursive type, and free instance constructor. So what about the co-algebraic type classes? Again, we pose the question in a similar way. If I have A and B, and I have their structure maps for a co-algebraic type class with the structure functor P, then what other type C can I find so that I can derive the structure map for C generically for an arbitrary fixed functor P? And again, I will ignore the laws. So in the case of algebraic type classes, we have the unit type. Now we don't. We have the void type instead. And that is certainly going to be possible. We can have a function from void to p void. We can have a function from void to anything. That's a function that's usually called absurd. And this instance will be lawful in a kind of vacuous and empty way, because any equations that this function must satisfy, it will satisfy, because there aren't any arguments you could ever give to this function. And so there's nothing to check. There's no case in which you could write down an equation that you could check. And so because of that, all equations hold. There aren't any equations to check. It's a vacuous. Now, I would say this is kind of not very useful, but formally speaking, this is a type class derivation pattern similar to the unit type for the algebraic type classes, which might be mildly more useful. The next is the pair, and it turns out that in the pair, only one of the elements of the pair has to be a type class member, and the other could be any fixed type. Because you can write a function like this by just taking A, you could transform A to PA, and then you fmap with this function that makes a tuple under the functor P, and then you're done. So but you cannot, so remember, in the case of algebraic type classes, we have the derivation pattern that's a function from D to A. And here we don't. We cannot do D to A for arbitrary P. The next pattern is the either. So here we can do this very easy, right? If there's A, you just take PA from the first structure map. If there's B, then you take PB from the second structure map. So that is how you implement them. But if you have AB in general, now what can you do? Well, you cannot map PA/PB into PAB. So the same kind of pattern that we had before, where we combine two instances into another one, it doesn't work, because you have to ignore one of them. So in other words, you have to use this pattern where one part of the pair is using the type class methods and the other isn't. So it's not symmetric like it was in the algebraic case. For some P, this will be possible to have a good and symmetric, useful derivation for the pair of two instances that in a useful way combines the operations on both instances, but in generally not. Recursive types, again, you have a fixed point and you assume that f, the functor f, preserves the type class membership. It's exactly the same case as before, just the code is a little different because we begin with C, we do unfix, we get FC, then we apply recursively h of r, which gives you a function fc to p of fc, and then you do fmap fix to do p of fc to p of c. So finally you get the value you need. And the final derivation pattern is the cofree type class instance. So the free instance is the one that exists for algebraic type classes, and it gives you a wrapper that creates a type class instance. Similarly here, you have a wrapper that creates a type class instance. Let's call it n. And now there's a different condition that there must be a unique type class preserving function of this type, not nc to c, but c to nc. Now this is a bit counterintuitive, but that's how it must be. There, nc to c you actually always have, and that's kind of trivial, and that's not interesting. The interesting part is that you should be able to get c to nc here, only for c that belong to the type class. And here are some examples. So cofree show, for instance. So show is the co-algebraic type class, so we can create a cofree instance of show by just wrapping it like this. And then to show this, you just take the second part of this tuple, you ignore the first part. So in other words, well, maybe not exactly very useful, but cofree type class instances are generally much less useful than the free ones, because the free ones is something from which you can compute stuff. There is this type class preserving function from the free instance to something concrete, this one. But so you can compute a value out of this. But for the cofree instances, the function type points in the other direction. So the cofree value is the final value that you have. And from that value, you still need to get something that's concrete, which is not obvious how you do that, and what you get. So what is the string that you get? So you can always map into this. So for example, how would you create this unique type class preserving function of this type signature for the cofree show? You take a type C that has a show instance, and then you take a value of type C, let's call it T maybe, value of type T, and then you compute show on that and put it here as the second part of the tuple. And that's how you create a value of the cofree show. Well, okay. Well, you could do that before. So what's the point of having this value? Well, in this case, now you don't need to know how to compute show on this, because you have already computed it and put it here as part of the data structure. So maybe this is somehow useful for serialization, I don't know. But in any case, this is not something that's so easy to figure out how to use. But I'm sure there are tutorials online to show you how to use cofree. Maybe somebody has figured it out. Cofree comonad. So comonad is a co-algebraic type class, and it has a cofree. It doesn't have a free instance. It has a cofree instance, which is defined like this. And this must use lazy pair, because otherwise it will immediately diverge. This is actually recursively defined, and it must be understood as a greatest fixed point. So lazily evaluated pair. Otherwise, you can't define it. So I just show this as an example of something that's not trivial, because this you can actually then derive. So like I said, in the case of algebraic type classes, if a type class has no laws, then it's very easy to define its cofree instance and free instance. So the free instance is just the free monad on the P, on the structure functor, and the cofree instance is a cofree comonad on the P. So if you take the show type class, And P for that is a constant functor returning string. And so if you put that in here, F is a constant functor returning string. So all this is gone. And this is just a pair of A and string. And that's exactly what that is. The cofree instance for show can be derived generically, but because it has no laws. But if the type class has laws, the show type class doesn't. But if a type class has laws, then it is non-trivial, very non-trivial to find what the cofree instance constructor is. I've seen a paper computing the cofree commutative comonad instance constructor. It's a bit of work. It's not easy. So that is concluding our overview of derivation patterns. So we have discovered the derivation patterns more or less just by trial and error. We tried several things and we saw when we can derive the necessary type signature for the type class from previous type signatures and when we cannot. And we see that for algebraic and co-algebraic type classes, they're quite different. And also we have stumbled upon these free and co-free constructors, which are mysterious. And in particular, they're mysterious because they use this type class preserving functions. And what is that? So the next part of my tutorial will talk about that.